What we're going to do today is basically, maybe I use the the slide later, but I'm gonna use the Blackboard mainly, and then if I really need to, I'm going to use the screen. All right, so I'm going to introduce the second half of the paper, not exactly the entire second half, but I'm just going to pick some of the most important part that is introduced in the paper. So the first question is, so how to implement Hadamard in surface code. And if we done this, what we can do is you can do more braiding. So how to use in surface code. So I'm going to reverse the order here. So because the paper actually introduced the grading technique in implementation of other gates, and then introduced the Hadamard operation. So I'm going to follow the order in the paper. So let's talk about the second topic and then go back to the first one. So I'm going to assume, so the first one actually doesn't depend on the second argument. So I'm going to assume that we can initialize any logical qubit as plus ket state. So plus ket state means, well, of course, it's 0 plus 1. So here, sometimes people use a bar or some other notation, like in the paper, they have a subscript large L to indicate that this is not a plus ket state in a single physical qubit. It's a logical qubit state. So, but I'm not going to put anything else than this, so you probably just consider this as a logical state. So the 0 ket is the logical 0 ket. So we talked about this, how to initialize the logical qubit into 0 in two different ways. One is the easy way, the other is the hard way. And easy way guarantees, easy way is very easy, but it doesn't guarantee whether it will be initialized as 0 or 1. But either case, if you want, then you just apply X logical gate to revert to whatever you want. And the hard way, you can initialize any quantum logical state, logical gate qubit into 0. Because then if you want to make 1, then you can just apply a logical X gate. But the question is, well, how do you make a superposition of two logical states? So now you need to go to the Hadamard operation on the surface code. So so for now, we're going to assume that we have some, whatever that is, Hadamard operation to make this logical qubit state. So we will explain this. Later. All right, so our first question is, how do we make CNOT gate between two logical qubits? So we talked about this with the Z-cut and X-cut qubits, right? So let me draw the picture again. Here we have so this is Z-cut and Z-cut. So here you could have a Z logical gate around this one of the Z-cut hole, and this is not the hole that you want to put the Z-cut Z chain here. So this line is where you could put X chain or X logical gate. But here and here, so this is the qubit 0, let's say, first qubit, and let's say this is another logical qubit, and it consists of X cuts. So in this case, This is not used as a hole whose boundary consists of X gates. This is the hole. You can put X, logical X, consists of physical X gates around the hole here, and you can put Z error or Z gates, logical Z gate, on this line connecting these two cuts. So we talked about how this is used, how this figure is used to implement the C0. So basically you want to make a braid, okay, like this. Okay? So basically if I write that as a quantum circuit, so each circuit, each register, this wire represents a logical qubit. So this is for the Z cut. So it's control. And the second one on here is X cut. It's a target. So it's one qubit state, one logical qubit state each. And what we are doing here is this, basically, right? So control qubit, control target, right? And because it's a braiding operation, there is another way of drawing this. So we are taking a loop around here. So so this is one way you can actually draw what's happening as a braiding. So still, this is Z-cut control qubit, and this is X-cut target qubit. So your control qubit is braiding over the target qubit, while your target qubit is not doing anything here, just staying the same way. So double line is basically because you want to braid, like making a knot between two registers. So that's why the paper draw these two lines, so like having a thickness here instead of this single line. And you can see that this kind of a knotting picture, like have a braiding here. So the paper gives a different color between this braiding part and the non-braiding part, but I'm going to just color the part where it's actually braiding here. Okay, so keep this picture in mind, and what we're going to do, so that makes sense, right? We kind of explained why this is true. So here we have one identity here, I, X becomes C, and I, X. So if you had identity operator here, which could have X here, but we didn't, and if you have X operator here, so X, the gate, logical X gate here, once you braid through, braid over this X cut, then it's still at IX, and which means that it satisfies one of the four identity that C0 gate must satisfy. And there are three more. So X, X, I becomes X, X, and I, Z becomes Z, Z, and Z, I equals to Z, Z, ZI, sorry, so I. So the paper introduced the first three in the picture, so maybe we can go for the last one. Actually, the paper suggests the reader to test out by themselves. So let's see. So we have a Z cut and Z cut. So if we have a Z and a control qubit here, then Z gate is around the Z cut here. And then we have X cut and X cut, and we didn't have anything, so we just have identity here. So we just braid over here. So that's our operation of C0, and see what happens. So this is the first picture, and let's say the after braiding, like all the way up to here, it's like this, right? So you could move the hole one by one, but you can make the hole larger so that it goes all the way around here. So then the next step is to just turning off this. So turning off all this Z gates around this boundary of big Z cut here by turning on the Z stabilizer inside. So then what happens? So this is picture 1, and this is the picture 2, and this is picture 3. So basically, so actually, I should have drawn it a little bit further down here. So maybe we should draw something like this. So here, this is the picture. So Z cut here. So your Z cut is actually around this empty hole, like empty cut here. So, and then what? So eventually what you had is you kind of merging that into here, right? merging it on here. So, and then you want to turn it off all the other places. You want to turn off the that stabilize. The Z gates around the boundary, all the other places except for this, except for here, right? By turning on that stabilizer, let's say around here, right? And then what happens is there was no Z gate or Z operator acting on this data qubit before, but because of this stabilizer turned on, there is new Z gate acting on this data qubit here, right? In these two, there were Z gate acting on here, but all the other places, because of these action, there were the Z gates acting on the data qubit boundary, but now it's turned off. So what happens is just you have Z around here, no, Z cut here, and then the X cut is still the same because nothing is done here, right? Okay, so yeah, so we have this, and okay, so you can also prove, let's see, you can prove 4 of this identity by just 4 bases of 2 qubit states. So for example, last identity is saying that Zi times C equals to C times Zi. What is it saying? So it says that there are two qubit operators, C0 and Zi. So this one is the control and this one is the target. And if you apply that to any 2 qubit state, then it is same as applying Zi first and then C0 gate. So let's see what happens. So when you have 0, 0, so first go through the C0 gate, then it's 0, 0. So let's say this is the control, this is the target. The left one is the control, the right one is the target, and that I is still 0, 0, and let's say 0, 1. Control makes 0, 1, and still it's 0, 1, and then 1, 0. Now it's control is acting on the target, so we have 1, 1. And when you have Zi, then we have minus 1, 1, and we have 1, 1, then the control gate, C0 gate makes it 1, 0, and then it makes minus 1, 0. So the left, this operator, this sequence makes 4 bases into these 4 bases. Now we only need to check is what if I switch the order of these operators and see if these 4 bases are transformed into the same bases in same sequence. Right? So if you have 0, 0, and then just put that into Zi, then it's 0, 0 again. So it goes to 0, 0. So basically it's the same. So let's check out the last one. 1, 1 goes to Zi, which is 1, 1, and C0 makes it minus 1, 0, which is same as the last one here. Okay, so it's easier. And also we talked about why this must be the only identity. I mean, I didn't explain it, but so it's intuitively clear. So the C0 gate, if you write that out in base 4, 4 bases of like these 4 bases, then it's 4 by 4 matrix, and it's Hermitian, which means that the dual is same. If you not the dual is the same, that if you multiply the dual, it's going to be identity operator. So basically, you only need to determine the so for elements, there are degree of 4 freedom to choose what the element or entry of this 4x4 matrix must be. And there are these 4 equations that is determining this for the variable of degree of 3 variables. So basically, it's enough. So you can, by just working on these 4 equations as a matrix, you can fully identify what Z is. Anyway, so that's the kind of summary of what we talked about. But today, the paper actually gives an interesting observation about another aspect of this C0 gate. So the question is, what if, so this C0, so this C0 is between Z cut qubit and X cut qubit. So Z cut qubit and X cut qubit. So that's the name that paper uses here. But however, what if we want to make a CNOT gate between 2 Z cuts or 2 X cut qubits? So the first one is, what if we have a 2 Z cuts? So basically, it means that we have Z cuts and Z cuts here. So if you want to do the same operation as we did here, then let's say I want to put I and X here, then I is the same, it has to be here. But here, the Z is, X is not on the whole because this is a Z cut, so these are Z cuts. So X is actually X cut, X. X is actually the line connecting 2 Z cuts. Okay, so it's a bit changed. So, and also you can see that the hole, the location of hole is off by 1 unit of length of this surface code, right? So the X stabilizer, this Z cut means that there should be a Z stabilizer inside, but here X cut means it has to be X stabilizer inside. So that and X stabilizer are off by 1 unit of length. So how do we make a CNOT gate between these two? So these are 2 legitimate logical qubits. I mean, you can just consider this as the first qubit and this is the second qubit. Now, the paper introduced that we can make a bit complicated situation, but using the first observation of C0, because this observation is very straightforward. So we're going to use this to make a C0 gate between these two. So here's the picture. It took for me some time to understand this, but I just want to share this with you. So we have so Z cut 4 register. Let me draw everything before I explain anything here. Okay, so we have, all right, so and then we have 0, plus, and we have name. So here, so I need to specify the types of these qubits. So these are all logical qubits. So they are not physical qubits, although it looks like a wire. So it looks like physical qubit. But like the situation here, we're going to assume that every wire represents a logical qubit, like this one's. But the top one is Z cut, and the second one is X cut, and the third one is Z cut also, and the last one is also Z cut. So it's basically 3 Z cut and 1 X cut. And oh, by the way, so yeah, sorry, so not here. Okay, so basically, all the CNOT gates, so there are 3 CNOT gates. All the CNOT gates are in between X cut and Z cut. So Z cut serves as a control and X cut serves as target qubit. So it's exactly like this situation. We have a Z cut as a control, X cut as a target. So using these 3 CNOT gate, and there's some situation that we need to consider here. So so we have a measurement on these 2 qubits. So basically, when you take the measurement, you see that that qubit is finished. I mean, we're not having any valid information stored in that qubit because we already measured and it corrupted and collapsed into the measurement outcome. So, however, because based on that measurement outcome, we decide whether to apply these special gates, Z and X. Also, this is logical Z and logical X because this logical qubit. And what happens is, while we have 4, okay, so we measure 2. The first control gate is here, the control, and we call it control in. So this is the input and this is the output. So this is control in, and this is targeted. So this is the control qubit, and this is the target qubit. But control qubit is the same control qubit when it's out, control out. But target out is different. This is target out. So what does that mean? So we're not keeping 2 logical qubits serves as control and target from the beginning to the end. So it's changing, the role is changing. So in the input, we consider this as 2 qubits that serves as control and target, but in the output, we're gonna take these 2 as our CNOT gate qubits. What does that mean? So control is the same, so we see this control qubit, but the target qubit state, whatever has been done to this target, because of these logical states of control qubit, the result will be stored in this qubit, in the target out qubit. Okay, so this target in qubit is no longer in use because we already measured. So it's just ruined. All the information that is going to be applied to the target will be stored here. So we have 2 sets of in qubits and out qubits. Okay, so but the role is changed. So that this is the picture. And you can see now why this is useful, because we can use this braiding 3 times, because every time we have a CNOT gate, we can take a braiding between this Z cut and X cut, right? So and also we have these 2 Z cuts as a control and target, 2 Z cut, still Z cut qubits serves as a control and target, right? So we kind of made a CNOT gate between 2 Z cuts. So let's see why this is actually CNOT gate. So here you have to observe that this is plus cat state, which can be only made by Hadamard application on 0 cat, right? So that's why I, in the beginning, assumed that we already have a Hadamard operation to make this plus cat state. Anyway, so let's see if this circuit serves as CNOT gate, then what we could expect is when we have a control in and control out, target in. So if control in is 0, 0, and control in is 0 and target in is 0, then after CNOT gate, the control out must be 0 and target out must be also 0. Right? But same thing. So if you have 0, 1, 0, 1, then the control in, control out must be same as 0. Target out must also be 1 because the control qubit is at the cat 0 state. But when it's 1, 0, now we're expecting that the X gate is applied to the target qubit. So the 0 cat must be changed to 1 cat, while the control qubit is same as 1 cat here. And if it's 1, 1, then it has to be changed to 1, 0. So all you need to do is just checking whether these 4 mapping is true in this circuit. So let's try with the first one and the last one. So 0, 0. So what's happening here? So I'm just going to follow the sequence, and I'm also want to explain about this measurement gate because it's not a simple measurement, it's a projection measurement. So let's say our control in target is 0, 0, so it's a 0, 0 plus 0. So I'm going to take the order of 0, 0 plus 0 from the left to right. Okay, so we have 0, 0 plus 0. That was the initial state in the beginning. And then what we have is the CNOT gate between the last one and the second one here. So look at the last one 0. So we don't do anything on the second one. So let's say we number this 4 qubits from 0, 1, 2, 3 here. So here we are doing C3X1, right? So we're not changing any state here because it's already 0. But then what happens is, okay, so we can switch the order here. So let's say this is the first because it doesn't really matter with what happens on the third, on the fourth one. So now we have control 0, x1. So look at the first one and then apply x to the second one here. So it's still the same because it's 0. Yes, so that's why we have 0. So we have 0, 0 plus 0. And then look at this one. Just take a measurement on the last qubit here. But we're taking measurement in the basis of x. What is the basis of x? It means that if you have one qubit state, there are two bases. I mean, the two types of bases. One is the basis in x, which is +1 state of -1 state of x gate. So measurement x is the measurement outcome in the basis of plus and minus. So whenever you take the measurement in basis x, then you're looking at the basis of plus ket and minus ket, which is the basis of one qubit state. So it's going to be either plus or minus because that's the basis, right? You're looking at the state to observe in a, let's say in a filtered lens. So you always get the filtered in the certain directions, the filtered light in certain directions. So your outcome will be always, measurement outcome will be always indicate whether the qubit is collapsed into plus ket state, which is plus ket, which is +1 eigenstate, and minus ket, which is -1 eigenstate of the x gate. And same for xmz here. So this is usual basis, because 0 is the +1 eigenstate of z, and 1 ket is the -1 eigenstate of z. So when we make this observation, we're not just taking measurement, which it always turn out to be 0 and 1. We change the basis. We kind of change the perspective. You can say that this is the projective measurement, just as we did in the stabilizer qubits. So anyway, so look at the last one. We're going to take a measurement here. So we can't measure 0, right? Right away in the basis of plus and minus ket, because 0 is a superposition of plus ket and minus ket. So we'll first take the splitting here, and then take a measurement. Then we have 50-50 chance of observing this or this, because it will always turn out to be plus or minus, right, with the equal chance. And let's see. So there are two possibilities that mx turns out to be 0 or 1. So if mx, the measurement outcome is 0, then this means that the qubit 3 is collapsed to +1 eigenstate, because we measured in the basis of plus ket and minus ket, and plus what is the usual sense. If you take a projective measurement, then whatever you get as a 0 is always +1 eigenstate. So therefore, your quantum state, which was originally the superposition state of these two, happens to be collapsed into this state, right? 0, 0 plus plus. So in that case, so what does that mean? So this is not really a legitimate drawing of the circuit, because after you take the measurement, it's gone. But what we have to do after the measurement is that based on the measurement outcome, we have to decide whether to put the Z gate on this third qubit or not. So if it's 0, if it's +1 eigenstate that is collapsed after the measurement, then we don't apply the Z gate. But if it's not, if it's 1, the measurement outcome is 1, which means that it's -1 eigenstate after the measurement, then we apply the Z gate here. So here we had a measurement outcome as 0, so we don't apply Z gate on the third qubit. So there's nothing here. So that's why I kind of draw this way, because it kind of looks like the control situation. So if it's 0, then we don't. If it's 1, then we apply it. So it's a kind of control Z gate here. But anyway, in this example, we don't have it here. But what we have is the control qubit, a CNOT gate between third and second. So look at the third. Oh, so on the third case, we have also the plus ket, right? So we don't know. So what's going to be? So we have to split this up first. So we look at the third one here. So it's 0, 0, 0 plus 0, 0, 1 plus, right? And then apply the CNOT gate. So look at the third one and decide whether to apply X gate on the second one. So here this becomes, in this case, nothing happens, 0, 0, 0 plus. And in this case, the 1 makes X apply to the second one. So it's 0, 1, 1 plus. So that's after the last CNOT gate. And what we do, we have the measurement set basis. So that basis means that we take a measurement based on 0 and 1 ket. So on where? The second one, right? So we just take the second one here. So also there is two possibilities, whether to observe this part, 0 or 1, right? So let's say we observe 0. What happens? We got this one. The state collapsed into here. So 0, 0, 0 plus. So in that case, the same thing happens, that we don't apply X gate on the third qubit. But if it's not, if it turns out to be the 1, the measurement outcome is 1, which means that it's stabilized at -1 eigenstate, then we apply X gate. But here we kind of assume that measurement outcome is 0, so this is the state, we don't apply X. So now the question is how to read this situation. So first of all, our beginning, the second and third is just in some sense auxiliary. So what we really want to look is the control and target, right? This is what is naturally given as a quantum state. But here in the second and third, we initialize the logical qubit into our special quantum state, 0 and plus. So this too is the control and target. I don't care about this 2 seconds because it's already initialized. So this is what we are given as the situation. And what we have to read at the end is the first and third, not the fourth. So first and third, this is what we have to look. So this is the control in, and this, sorry, not in, so out. This is the target out. So compare the control in and target in. So we have control in and target in. Okay, 0, 0. What happens to the out? Control out, target out, 0, 0. So it satisfies our CNOT gate mapping. 0, 0 goes to 0, 0. Okay, that makes kind of obvious, right? I mean, it looks like it's kind of a coincidence. But let's see what happens. So there were 2 choices of the measurement outcome, but we just choose. So actually, there are 4 choices because there are 2 choices for each measurement outcome. Among these 4, I just chose 1, very special kind. So let's see what happens if I choose different way. So let's say my measurement outcome is 1 instead. So in this case, I observe this, right, instead of the first one. So my quantum state is 0, 0 plus minus. But then what do? I apply Z-gate on the third qubit. So I need to take Z3 here. So then what happens is it becomes to 0, 0 minus minus. Right? Plus ket becomes minus ket after that operation. So and then we take the third. So we are at this stage, and then we apply C0 gate here. So look at the third qubit here. We have 0, 0, 0 minus, minus 0, 0, 1 minus, and then we take a last measurement in base of Z, right? So let's say in this case, we take another case that MZ could be 0, I mean, anything can happen, but let's say MZ is 1, then what happens? Our situation means that this is chosen, right? So it has the 4 quantum state, this 4 qubit state is now collapsed into 0, 0, 1 minus, right? But then what happens is, because of that measurement outcome is 1, we apply X gate on the third qubit. So X3 is applied, and the third qubit means X2, sorry, so X2. See, same thing here, it's at 2 here. So the third qubit here, so the label is 2. So and then what happens? 1 is turned to 0, so this becomes minus 0, 0, 0, minus. Okay? So here again, we read the first and the third, because that's the control out and target out. The same result, 0, 0, and 0, 0 here. So you can check whether the all other cases are actually the same. So let me do one more. I hope that I have time. But what if we have, instead of 0, 0, maybe that's too simple. What if we have 1, 0? So 1 for the control and 0 for the target. So in that case, let's see. We start from 0. No, not 0. So 1, 0 plus 1, right? So that's our initial stage. And then after control qubit, C3x1, right? So then I look at the C0 gate here. So C0 gate on the third qubit, not the third, the last one, sorry, the last one. Yeah, so C3, so it's the last one. So because of this, I apply X on the second qubit, which is the qubit 1 here. So we have 1, 1 plus 1. And then we take a measurement. Let's say we take C0 gate, another C0 gate here, C0x1. So C0x1. So again, another X gate on the qubit 1. So we have 1, 0 plus 1. And then let's look at the measurement basis. So we are taking a measurement here with a basis of X, right? So it has to be, no, the last one, right? So the last one we have on the last one here. So we need to take the superposition between 1, 0 plus plus minus 1, 0 plus minus, right? So let's say our measurement outcome is 0. So that means our quantum state is collapsed to here because it's plus 1 eigenstate. So 1, 0 plus plus. And then what we do is don't apply that gate on the third qubit, and then we just jump into the C0 gate from between third and second. So we have C2 x1 here, so C2 x1. So now we also have to write that out in the superposition. We have 1, 0, 0 plus 1, 0, 1 plus here. So when you apply the C0 here, then it's doing nothing on the second qubit, qubit 1. And here we change the 0 to 1, so it becomes 1, 0, 0 plus 1, 1, what? 1 plus. Okay? And then we take the last measurement on the second qubit. So here or here, right? It could turn out to be 0 or 1. If it's 0, let's say, MZ is 0, then it's collapsed to this state, 1, 0, 0 plus. Okay? then that's over, because in that case we don't apply X gate here. So if it's 0, don't apply it. Now, it's the same situation. So we start from these 4, but the important is the target in and control in. The control in 1, target in 1. What has to be the target out? The target out must be 0, because control is 1, then we apply X to the target, so the target out must be 0. So where is the target out? The third qubit. So this is target out, and control is the same. So it's 1, 1 becomes 1, 0, just as CNOT gate. That makes sense? So, I mean, we could go for all the possible choices, but it works. So I'm not sure whether this is the original finding in this paper or not, but they found this. They found cleverly by doing this braiding, then they can make a CNOT gate between these two Z-cut gates, Z-cut qubits. So let me introduce another thing. So the paper actually omits this part, so I kind of spent some time to find this out by myself. So what that is how to make CNOT gate between two X-cut gates, X-cut qubits. I hope this is right, but I checked a few. So here, let's see. So the third case, CNOT between two X-cuts. Okay. What happens is we have X, so we have 4, basically 4, 1, 2, 3, 4, and then we have X-cut, X-cut, and Z-cut, and X-cut. So these are 4 nature of these logical qubits. So we prepare 3 X-cuts and 1 Z-cut, and there are roles of each X-cut and Z-cut. So this X-cut is control N, and this X-cut is target in. And the nature doesn't change, but on the other side, I'm making this X-cut as a control out, and the same X-cut, this X-cut, as a target out. So the situation is a bit different. Here we had 2 different logical qubits serves as a target qubit and target in qubit and target out qubit. Here we have 2 logical qubits serves as control in gate, in qubit, and control out qubit. But the target in and target out stays the same. And the circuit looks like follows. So we have first initialize these 2 qubits as this, and then we have here, and then we take a measurement. The base is upset, and then based on the measurement outcome, if it's 0, then we don't apply X. If it's 1, then we apply X, just like CNOT gate, and then we apply CNOT gate between these 2. And then here it's a bit, this is what I found here. So we have another measurement gate that is based on Z operator. And then it seems like to me the paper doesn't explain fully about this situation afterwards, but it looks like to me that if the measurement outcome is 0, then you have to apply X gate here. If it's 1, you don't apply it. So that's why I put the tilde above this MZ. So I found that this works. So the paper actually gives no information about when to apply these X gates, but I just wrote it in just as this picture. So here we have target out. So what do we have here? We have control in, target in for the second qubit and fourth qubit. Now the target control out and target out is the first and the fourth qubit. And between there is 2 qubits collapsed because of the measurement that affecting something on the other qubits on the control and target here. So Let me go back here if I have time to check a few cases if it actually works. So for now, what I want to explain is how to make this CNOT to make more complicated gate. So for example, so this is basically 2-qubit gate. If you have 2 logical qubit, how to make CNOT operation between them, right? But you have a situation where you need to make a multi-control or multi-target qubit gate. So for example, how do you make topology gate? So topology gate is basically when you have a multiple control gate. So this activate the X gate on this qubit only when these 2 control qubit is at the Cat1 state. So this multi-control. And also you might want to activate this. So basically you can actually make 2 CNOT gate, but let's say I want to make it 1. So based on the control qubit here, I want to activate both of these X gate on these 2 target qubits. So multi-control, multi-target. So how to make this? So we are going to make a braiding part. So I'm going to draw something here, just like I draw in the beginning as a braiding. So here, whenever you have this CNOT gate between logical qubit, which is given by Z cut and X cut, you can make a braiding. So let me take a braiding here. Okay, so I make a loop closed on this side because it's over, because it's not, any information on this qubit is not preserved anymore because it's finished after the measurement. And what other braiding could happen? So we have the thing on here, right here, and also in here. Let's see, it still survived, right? This one is survived. So we have braiding going above here, right above here, right? So these are 3 things. And how about this? So we have. Let me use another color, the blue color here. So let's see. So we have these thing going on the blue part. Okay. So by the way, so I'm gonna close this out too. So I'm gonna close. The closing means that the qubit is either initialized or collapsed because of the measurement, so which means that we don't allow the general quantum state. We kind of manipulate it in the beginning or at the end. So here we manipulate it at the end, or also we manipulate the qubit by initialization. So it's closed from the beginning and the end. So it's kind of closed loop here. But all the other qubits, it's kind of half loop or it's infinite loop. Not half loop, yeah, half loop or just infinite open here. So you can depict the situation of this CNOT gate between 2 Z cut using braiding. So we have one braid, the yellow one on top, braiding over this blue one and blue one here. You see this 3-dimensional picture, kind of 3-dimensional, like one string is over on the other, right? So it's kind of braiding over. Makes sense? Like it's a common notation when actually the mathematicians make who's studying braiding or knotting here. So we have another braiding over this loop, the blue loop from here, and another braiding over loop here. But now there's a very interesting thing that you can make it simpler. Just ignore all the information about this quantum circuit. Make it simpler. So you have one big loop here. You can make a loop, change the shape of a loop by shrinking it, right? So it's going to be kind of chained on the left side of this blue loop, right? This yellow part is chained on the left side, and this yellow part, it's closed here. So if you just shrink this part all the way up to the right side of this loop, the blue loop, that is on the chains on the right, and on the top, it's chained on the middle here. So I can make this like, let's see. Let me erase this. I can make this as the following. So we have blue one sticking out, which is loop, and the yellow one on the right, on the left, and another yellow one on the right, chained here, and on top there is another one. So the yellow one is the Z cut and the blue one is X cut. And this means that it's it's a CNOT gate between the Z cuts. Okay? So whenever you want to make so also what's on the left? What's chained on the left? The blue loop. It's a target in. So we have target in. And what's chained on the right? It's target out. And what's on the top? It's control in and out. Right? So each loop or strip represents a qubit, logical qubit. Right? So including blue one, there are 4 logical qubits involved here. And the blue one actually doesn't do anything, but it's kind of chaining everything, every other Z cut through this braiding operation. The yellow one serves either a control or target. It could be in and out, or it could be in or out, right? So now that this is the situation, let's look at this one. I also want to make a picture like this. So we have a braiding. So whenever you have a control, it's kind of braiding over. So we have Z cut here, Z cut here, and Z cut here. So it's over here, so it's going to be closed here. So how about here? So it's closed here, so it's closed loop here. And here it's going on, so it's just open loop here. And then this one is, no, it's not open, sorry. So it's closed here because it's initialized here. So this is open, so this is open, open all the way, okay. So, oh, okay, so this is closed on here because it's initialized. So let's make a picture of this one. So what does it look like? So we have, so instead of the blue one over the yellow, so we have a yellow over blue one. So we have the yellow one is sticking down here. Maybe make it thicker. So we have the yellow one here, and the blue one on the bottom is actually braiding around here, the yellow, and the yellow one is a closed loop. So we have a closed loop here, and on the let's say I'm shrinking this loop so that it makes a simpler picture. So we have control in gate looping over the left part of this yellow chain, yellow loop. So it's here we have looping here, and also on the right we have on the right the control out, right? So we have control out and this part. So if you're just shrinking thing over here, then this control out, the blue half loop, is chained on the right side of this yellow loop. So let me name this. So this is control in and control out. And this is target in and out. Okay. So the paper introduces using these braiding, you can make the multi-qubit, multi-target or multi-control CNOT gate. How? So how do you make this one? So this one have multiple control. So and the single target. So I want to go for this picture. No, not this picture. So this picture. So I have a multiple control. So I have multiple, let's say 2 control over here, 2 control. Okay, so I don't want to close this out because control qubit is still, it has to be the same. I mean, I don't take any measurement on the control qubit, so it has to be open strip here. And also on this part, but what I want is having one target, say target. So I want the information on the target qubit continued. Even though the qubit is changed, the logical qubit is changed in the input state and output state. So it's a target in and this is target out. And then this is control 1, and control 2. And how do you make braiding to make this happen? So whenever you look at the picture here, so you have a control and target, and you just take a loop of Z cuts here, of X cuts here. So then you make, you have, so let me make it this way. So we have, the picture must be a little bit shorter here. So anyway, so we have us over here, and then braiding over. So we have here all the way up to here, and then all the way up to here. Okay. So this X cut is braiding over target in, target out, and also control in, control 1 and control 2. Okay. So then you can make a double control C0 gate. So which is topology gate. But how can you make this opposite situation? So you just reverse the situation. You have one control, so you have one control, so you put the control in and control out, and then multiple target in the bottom. So let's see, it's too big. So let me draw it here. So this situation can be drawn like we have, let's see, blue ones, right? So we have a blue one, and so these are X cuts. So, and then we have, and then we braid it over. So we have these braiding. Okay. So this is, now we are using the second picture, which is C0 gate between two X cuts. So these are X cuts, and the blue ones are X cuts. And so this is control in, control out, and this is target in, target 1, target 2. Okay. So you can increase the number of targets or number of controls as many as you want by doing this. Just make more braiding, but still keeping the same number of X cuts or Z cuts there, Z cuts and X cuts there. Just take a braiding. Then you can make a multi-qubit, multi-target, multi-control C0 gate. This is a very clever idea. And what we are left to do is how to make, so the important thing is that when you use this, you always need to know how to make the plus get state, right? So our question is how to make plus get state, which means how to make a Hadamard operation on the surface code. So this is also easy, and not easy, but it's doable. I mean, not as complicated as this. So let me introduce by just drawing it here. So you either start from X cuts or Z cuts. Let's say we start from Z cuts. So we have Z and X. Okay, and I advise you to have a paper opened up side by side to understand this situation. What we want is we want an operation that satisfies these two identities. So whatever H is, if it satisfies these two equations, then it is the Hadamard gate. Okay, so same as C0 gate. So what we do, so in C0 gate, we kind of did the braiding, which doesn't seem like anything similar to great gate operations, because we didn't do anything on the target qubit or physical qubit, but just simply make a hole changes its positions, and then the result is the same effect as the C0 gate is applied. So that's the idea, the same spirit that we're going to use here. So we're going to make this into, this. It's very interesting. So how could this XZ becomes ZX? So what I mean by this hole is the same hole, same place. The hole holes are the same place. So exactly the same configuration, but this X and Z are switched, completely switched. How can this possible? So actually, we are changing the role of data qubit and stabilizer qubit in this process. So even though we are looking at the same figure, we're kind of changing the configuration of surface. So here's the idea. So and then why? So whatever we do in this process, why this serves as Hadamard? Because Hadamard, when you change the perspective of looking at the quantum state, it changes the X gate to Z gate and Z gate to X gate. So basically, we changed X gate into Z gate and Z gate in Z operation in the X operation. So we can consider these processes whatever corresponds to the Hadamard operations. All right, so how do we do? So first of all, we take an island of a surface code. So imagine there is an infinite surface code in this board. And then we just cut through some small trench around this island, or trench or whatever. So like a water flowing around the castle in the medieval area. So we have a empty the stabilizer that is turned off around this island. Okay, so it's kind of separated surface code, and then we take a half of this just through this X chain here, and then turning on all the Z stabilizer inside this half here. So turning on all the Z stabilizer here. So it's a hole here, so you don't turn on here, but all the other Z stabilizer is still survive, still valid. So just turning on those, and then what happens is all the data qubit inside of this side is having two gates because of the two stabilizer connected to that data qubit. But here, the data qubit around the boundary is now canceled out, so there's nothing on here. But on this boundary, now you have this Z stabilizer, Z gate applied. So now what you did by doing turning on the Z stabilizer is moving your Z gates or logical Z gate into this Z chain. Okay. So and then what you do is cutting more smaller picture here. So let's make it bigger. So what happens here is, where's white? Okay, so white is. So you have to start from the big picture. So that's why the paper actually start with a very large surface code. If you look at the paper right now. So you cut through this, and then you have Z chain, and you have X chain here. And then you do something interesting. You turn on all Hadamard, so apply Hadamard, apply Hadamard on all data qubits. Apply Hadamard on every data qubits. So now what happens is, magically, kind of magically, so not magically, it's a mathematics. If you look at everything in the Hadamard basis, like say if you had a basis of 0 and 1, but you applied Hadamard on that qubit, then what you do is you actually changes the basis of the observation. So you were observing the data qubit in the basis of 0 and 1, but after you take the Hadamard, let's say you apply the filtered lens on the light, then your basis changed to plus ket state and minus ket state, right? So your action of X gate and Z gate have now completely switched, because when you were in the 0 and 1 basis, your X makes 0 to 1 and 1 to 0. But now, when you apply it to plus and minus, so plus is just plus and minus is minus ket here. So what you're doing here is, since I changed the basis, but I don't want to remember the old basis, so I want to think about this plus ket as my 0 ket, the ground state here, and minus ket as my excited state, which is ket 1 ket state. And then what kind of operation does this? What kind of operation does this? So 0 goes to 0, 1 goes to minus 1. That's not x, that's actually z, right? Z is doing this. So by applying Hadamard, you're changing the basis, therefore you're changing the role of x gate and z gate. So your x is no longer x, it's actually z, and your z is actually x. So x is here and z is here. And now the problem is they're a bit off. I want to make it in the same position as before. So what you do is, let me make a picture a bit on the corner let's say on this corner here. So on this corner, what happens is you have a data qubit and you have a stabilizer qubit, and so on. So and then there is another stabilizer. I mean, there is qubit right next to this corner, but we just turned off, right? We turned it off, right? And there is another qubit right above this data qubit. We just turned it off, but the qubit is there. So what we do is we exchange the quantum information between these two qubits. Or what do you mean by that? Okay, so there is a quantum information stored here. There is a quantum information stored here, right? There's a swap operation. It's not cloning, it's a swap. You can swap quantum information between any two qubits. Swap operation is always possible if you have some the nearby qubit. So you just swap the information here, right? So this now becomes the data qubit, and this becomes the stabilizer qubit because it's swapped, right? The role is changed, but also the information is swapped. And then what you do is, you also swap the information from this one and this one. So now, after you're swapping these two information, this has the original data qubit information, and this one is just random data stored in the stabilizer qubit here, but you now switch it to over here with this stabilizer qubit. So this stabilizer qubit has now information on this data qubit, which is now the stabilizer. It was originally data qubit, but now it's a stabilizer. So, and then you do this for every qubit to the left, right? So you kind of switch it to the 1 unit by shifting everything to the 1 unit of this length. And then after that, you switch it with the qubit right above here. So you just switch the information about between these two qubits and so on. So you kind of make it with one shifting to the left and top by 1 unit of length. And then remember that these were actually inside of this surface code, right? So it's now bit here, around here. And then you start to turning on all the other qubits around this small island. It's an island inside of island. And then you make it switch back to original configuration as before. So we have like the X and Z, but then I want to make it into this configuration. So turning on the other, just reversing the whole process that we had before. It's just turning on half, or turning on everything except this two hole, and then turning on these half here. So make chain becomes a loop here, and then basically get this. I think the book explains the situation where you actually get the exactly same configuration, that Z is here and X is here. But nothing seems like nothing happened. But what really happened is because you apply the Hadamard. So this is the important part. You apply the Hadamard on the data qubit, so you actually change the role of X and Z. So the information, the logical qubit stored in this 2 Z-cut qubit, or 2 Z-cut qubit, is now, if it were plus 0 ket, then it's now stored as plus ket, because inside what happened is the operation that changes the role of X operator and Z operator. Okay, so that's why you can initialize any logical qubit as a plus ket state. So by the way, so along the process, what we are doing here is every time we do anything on any data or stabilizer qubit, we keep track of error. That's the important part. We take the cycle of surface code and then keep track of all the errors possible. Even when we turn off the stabilizer to make an island, we take the measurement on the boundary so that if there any error on the data qubit nearby, then we keep track of it. So we don't minimize the loss of information in the process.